VLSI. Hope you're all doing good. Yeah. So I hope my screen is visible and my voice is audible. So let us start today's session. So in today's session, we will start with the topic called full wave rectifier. Okay. So in previous session, we have discussed about full wave, half wave rectifier. We will see how to uh, design a full wave rectifier. Okay. Yeah. Let me share my screen. So basically, in our half wave rectifier, this was our output what we were getting. So only the half positive cycles were, that we were getting. So now let's start with the full wave rectifier. Full wave rectifier. How to design a full wave rectifier using the diode. So first let's see the input and output of our full wave rectifier. So let's say this is our full wave rectifier FWR, and let's say this is our input voltage. This is our input voltage. Okay, sinusoidal input AC voltage, and the output of this full wave rectifier will be a pulsating DC. Will be a pulsating DC. So like this, we will get our output, which is a pulsating DC. Okay, and the frequency of this output is 2 input, whereas in case of half wave rectifier the frequency was same, but in the case of full wave rectifier the frequency increases. Okay, now before starting about the full wave rectifier, we will see one circuit diagram which is with a transformer coupling. Okay, so let us start with this topic called transformer coupling. What if a circuit consists of this transformer coupling? How to analyze the voltage, that we will analyze, and then we will start with full wave rectifier. Okay, now let us have a voltage source at the input. This is V in, and we have a fuse here, and transformer symbol is represented by windings, right? This is our diode. Okay, in our previous sessions, we haven't seen this type of transformer coupling. We have directly connected our input source to our diode. Okay, we have directly connected our input source to our diode, but from this session we are going to see with the transformer coupling. So diode is not connected directly with the input voltage source. It is, so this is fuse, and this side is primary side, and this is second. Basically, this transformer is often used to couple the AC input voltage from the source to the rectifier. We use this transformer coupling. Two advantages. First advantage is to allow the source voltage to be stepped down as needed. So the voltage of the source can be, AC source is electrically isolated from the rectifier, preventing any kind of shock hazards in the secondary circuit. So for that, we are going coupling to either step down the the voltage, input voltage, or to either step up the input voltage also. We can, that we already know. And side, let us declare it with ERI. Okay, this is number of ERI. Okay, this is number of turns in the primary side, and N in secondary side. So NPRI is the number of turns in the primary side, and N second is the number of turns in the secondary side. Okay, now so let's say a transformer. So let's say A transformer with a turns ratio less than 1 is a step down transformer. Okay, I will write it here. Transformer with with turns ratio less than 1 is step down transformer, and greater than 1 it is a step up transformer. So the relation between the secondary and primary is given by V secondary is equal to N into V primary, where V secondary is the secondary voltage and V primary is the primary voltage, and here N is the turns ratio. Okay, the secondary voltage of a transformer equals to the turns ratio N times. N is the turns ratio. If N is greater than 1, that means the secondary voltage is greater than the primary voltage, and if N is less than 1, my secondary voltage is less than the primary voltage. It's obvious, it can be seen from the equation also. So if the number of turns in the primary side are more and if the number of turns in the secondary side are less, then the voltage is getting to decrease. And if number of turns in the primary are less and more in the secondary, then the voltage is going to increase. Okay, and it also can be given by the equation V secondary is equal to N into V primary. That is, if N is greater than 1, V secondary is greater than V primary. That is a voltage, that is a secondary voltage is greater than the primary voltage, and if N is less than 1, then the secondary voltage is will be less than the primary voltage. Okay, secondary voltage is nothing but the voltage which is appearing on the right hand side. This is secondary voltage, that is the voltage which is going to given to our diode, and this is our primary voltage. On the left hand side is our primary voltage, that is we are getting from our voltage source. Okay, now let us start the discussion of our full wave rectifiers, how our full wave rectifier works, everything we will discuss. Okay, we will discuss our full wave rectifier with a center tapped full wave rectifier. Okay, we will discuss our full wave rectifier with a center tapped circuit, center tapped full wave rectifier. Let me draw this diagram. This is my fuse. These are my primary windings, and this is my secondary winding. And this is diode 1, and this is my diode 2. And from here my load resistance is attached, RL, which is connected to ground. Okay, this is diode 1, this is diode 2. Okay, and this is a center tapped transformer. Center tapped transformer is nothing but let's say this is our primary voltage, V primary, and this is our secondary voltage, V secondary. V secondary. So in a center tap transformer, if we use a center tap transformer, then what happens is the voltage, the secondary voltage is divided equally. So in a center tap transformer, the secondary voltage is divided equally. That is, here it will be V secondary by 2 and this side V secondary by 2. That is meaning of a center tap transformer. So in a center tap transformer, the secondary voltage will be divided into two portions, equal portions. Okay. Now here we are applying our input voltage. Okay, this is V input, and here we are going to get our output voltage, V out. So the positive cycles, if you observe, are the positive cycles of input Okay, at the positive input cycle, what happens? At the positive cycles, here it is given this D1 will be forward bias, right? And D2 will be reverse biased. Why? Because here it is a center tap transformer, so the voltage polarities will be okay. So before that, so for a positive half cycles of the input voltage, the polarities of the second voltage are will look like this. I will draw it here. So it will be plus and minus, and here it will be plus and minus. Okay, and this condition, the forward bias diode D1, so the D1 is forward bias and the reverse the diode D2 is reverse biased. Okay, here plus and minus. Okay, here if you observe plus minus, I will draw it in a neat manner. 1 minute, let me erase this. Okay, so here the voltage source, the voltage polarities, if you observe carefully, plus minus plus minus. Okay, and plus is given to the anode, and here the minus is given to the anode. Okay, this is D2. If you observe the voltage source, the negative polarity is given to anode for the D2, so that's why in this case it is reverse biased. In this case it is reverse biased, and here it is forward bias. What we are talking about, the input voltage when it is in positive half cycle. In positive half cycle, due to this polarities, the D1 is in forward bias and D2 is in reverse bias. Okay, when the negative half cycle comes, when the input negative half cycle comes, then the polarity gets reversed. That is, here we will get minus, here we will get plus, and here we will get minus, and here we will get plus. So this positive voltage is given to the D2. This positive voltage is given to the D2. Then D2 will act as the forward bias and D1 will act as reverse bias. So since we are using this center tapped transformer, what is happening? And I will write it here. At positive input voltage, that is positive cycle of input voltage, our D1 is in forward bias and D2 is in reverse bias. Our D1 is in forward bias and D2 is in forward bias. If you observe at the positive half cycle, here the polarity is plus and minus, plus and minus. So plus is given to anode and here anode. So that's why it is reverse bias and this is in forward bias. And now what is happening? When a negative voltage, negative half cycle comes, I will write it here. Negative half cycle, the polarity changes. It will be minus plus minus plus. So plus is given to D2, positive side is given to D2. So that's why D2 will be in forward bias. D2 will be in forward bias and D1 will be in reverse bias. So for every cycle, the D1 and D2 will change. Once it will be in forward bias, and for another clock cycle it will be in reverse bias. The D1 will be forward bias in a positive half cycles only, whereas in D2 will be forward bias in negative half cycles of input. Okay, whenever the input whenever there are negative half cycles in the input, the D2 will become forward bias, whereas there are positive half cycles in input, the D1 will become forward bias. So whenever the D1 or D2 are in forward bias, they start conducting the current. Okay, whenever the D1 or D2 are in the forward bias, the current conducts through that particular diode. What happens if the current conducts through that particular diode? Then the voltage drop will be observed on this resistance. That is, we will get the output voltage. So that is how a full wave rectifier works. For example, if we have an input voltage like this, right? So for this input voltage, For this positive half cycle, our D1 conducts, diode D1 conducts, and a voltage drop will be observed at the load resistance RL. Here D1 is conducting, and at the negative half cycles, the D2 will conduct. Similarly, again D1 will conduct, followed by D2. So like this, the voltage drop will be observed at the load resistance. So for positive and negative half cycles of the input, we are getting the output voltage. We are getting the output voltage. So that is what a full wave rectifier. Okay. So this is the operation of a full wave rectifier. Okay. I hope it is clear. Now let us see the effect of turns ratio on output voltage. Now let us see the effect of turns ratio on output voltage. I will write it here. So if the transformer's turns ratio is 1, then the peak value of the rectified output voltage equals to the half of the peak value of the primary input voltage. So if the transformer's ratio is 1, then what happens? Then the output ratio will be half of the, the output voltage will be half of the input voltage. The output peak voltage will be 1 by 2 of input peak voltage. Why? Because if you observe here, if you are giving the input voltage we are giving here, the input voltage is getting half. Okay, this half voltage is only, okay, this here this half voltage is applied, and here it is again divided into half. So this is Vp, then it will become Vp by 2 and Vp by 2, and this voltage drop is only observed at the output. So if turns ratio is equal to 1, then if the input peak voltage is Vp, then output voltage will be equal to Vp2. So this is how the turns ratio is going to affect the output voltage, the output peak voltage. Okay, so that is about full wave rectifier and the effect of turns ratio on the full wave rectifier, and about the center tab full wave rectifier. I hope this video is clear and you have got a clear idea about what is meant by full wave rectifier and how a full wave rectifier operates, and how this turns ratio and transformer ratio is affecting the peak output voltage, everything. Okay, yeah. So that's all for this session. If you like this video, please like, share and subscribe to my YouTube channel all about VLSI. Thank you.